All right, let's get into it. All around us right now, there's this invisible, slow-motion war being fought. It's a battle that's happening on our cars, our bridges, even deep inside our electronics, and it costs us billions. I'm talking about corrosion. And in this explainer, we're going to pull back the curtain on the science of rust and explore the really brilliant ways we've learned to fight back.
At its very heart, corrosion isn't just decay. It's a fundamental force of nature. And this quote, it just nails it. Think about it. We pour all this energy into digging metals like iron out of the ground and refining them into something pure. Well, corrosion is just nature, patiently, relentlessly, trying to pull those metals back to their original state, back to their comfortable, stable ore form, like iron oxide, which we know as rust.
So how does nature actually do it? Well, the secret is surprisingly electric. It turns out, any piece of metal that's corroding is basically acting like a tiny, self-destructing battery. And to figure out how to stop it, we first have to understand exactly how this little battery works.
Okay, so here's the official definition. But the key word, the one you really got to focus on, is electrochemical. This tells us that rust isn't just some simple chemical stain. Nope, it's a whole process that involves the flow of electrons, an electrical current, just like in a Duracell. It's an electrical event happening on a microscopic scale.
For this little corrosion battery to even switch on, you need 4 essential things. Think of it as a recipe for disaster. First, you need an anode. That's the part of the metal that's actually going to get eaten away. Second, you need a cathode. This is the part that stays protected. It's where the electrons want to go. Third, you've got to have an electrolyte, which is usually just a bit of moisture that connects the anode and cathode. And finally, you need a circuit, a path for those electrons to flow, which is the metal itself. Here's the kicker. Take away any one of these 4 things, and the whole process just stops.
So here's the play-by-play of how rust is born. First up, the metal at the anode starts to literally dissolve, and as it does, it releases electrons. Those electrons then need somewhere to go, so they travel through the metal, that's our circuit, over to the cathode. Once they get to the cathode, they react with oxygen and water from the air. And for the grand finale, the dissolved metal ions from the anode meet up with the new stuff created at the cathode, and boom, they combine to form rust.
But here's the thing. Corrosion isn't a one-trick pony. Not at all. It's got a whole playbook of different attacks it can use, all depending on the situation. And if you want to pick the right defense, you absolutely have to understand these different forms.
Let's look at 2 of the most common types. On the left, you've got pitting corrosion. This can happen on a single piece of steel. Say a drop of water just sits there. The spot right underneath that drop gets less oxygen than the area around it. That low oxygen spot becomes the anode, and it starts to corrode, digging a nasty little pit into the metal. Now, on the right, you have galvanic corrosion. This is totally different. It happens when you connect 2 different metals. The more chemically active or unhappy metal becomes the anode and basically sacrifices itself to protect the other one. A classic example is putting steel bolts on a copper plate. The steel will rust away like crazy.
And make no mistake, the stakes here can be incredibly high. Just look at something called caustic embrittlement. Inside high-pressure industrial boilers, slightly alkaline water can sneak into tiny cracks in the metal. Then it evaporates and becomes super concentrated. This nasty concentrate then attacks the very grain structure of the metal, making it brittle. The result can be a sudden, catastrophic failure. It's a terrifying reminder that this whole battle isn't just about a little cosmetic rust.
Okay, so we've met the enemy, we know its tactics, now how do we fight back? This is where the engineering gets really, really clever. We have developed an entire arsenal of techniques to stop corrosion dead in its tracks.
So remember how only the anode corrodes and the cathode is always safe? Well, that's the key. Cathodic protection is this absolutely brilliant idea of forcing the entire structure we want to save, like a huge pipeline or a ship's hull, to become the cathode. Because if it can't be an anode, it simply can't corrode. It's so simple, but it's genius.
And there are 2 main ways we pull this off. First is the sacrificial anode method. This is like providing a decoy for the corrosion to attack. You bolt a block of a more active metal, like zinc, onto a steel ship hull. The zinc willingly becomes the anode and gets eaten away, sacrificing itself to save the steel. The other way is impressed current. This is more high-tech. It uses an external power source to constantly pump electrons into the structure, basically force-feeding it so it can never lose its own electrons and become an anode.
This very same principle explains why some metal coatings are way better than others. A galvanized steel bucket, for example, is coated in zinc.
Zinc is more active than steel, so if you scratch it, the zinc right next to the scratch acts as a tiny sacrificial anode protecting the exposed steel. We can call that a good scratch. But a classic tin can is coated with tin, which is less active than steel. If you scratch a tin can, the exposed steel becomes the anode, and believe it or not, it actually rusts faster than it would have on its own. That's a bad scratch.
You know, sometimes, instead of adding a whole new layer, we can just beef up the metal's own natural defense system. Aluminum, for instance, naturally forms a thin, protective oxide layer. Anodizing is a process that uses electricity to make that natural layer incredibly thick, hard, and durable. And as a cool bonus, this new layer is porous before it's sealed, so you can actually dye it. That's why you see aluminum in all those bright metallic colors.
And that brings us to our most advanced defenses. Plating isn't just about stopping rust anymore. It's about giving a basic metal entirely new superpowers, making it tougher, more conductive, or just drop-dead gorgeous. So the classic method is electroplating. It's this beautifully controlled process. You take the object you want to plate, let's say a regular steel spoon, and you make it the cathode. A bar of your coating metal, maybe pure silver, becomes the anode. Then you dip both of them into a special bath that contains a salt of the coating metal, like silver nitrate. You flip a switch, apply a current, and just like that, the silver anode starts to dissolve, and those silver ions travel through the solution and deposit themselves in a perfect, shimmering layer all over the spoon.
But what if your object has really tricky shapes? Or what if it isn't even a metal? Well, that's where electroless plating comes in. This is like a form of chemical magic. It deposits a metal coating using a chemical reaction right in the solution. No electricity needed. And the huge advantage is that you get a perfectly uniform layer, even deep inside tiny holes. And get this, you can even use it to plate non-conductors, like plastics.
And this isn't just some niche trick. It's absolutely critical for modern technology. Think about the circuit board inside your phone. It's mostly non-conductive plastic, right? To connect the different layers, they drill thousands of tiny holes through it. Electroless plating is then used to deposit a micro-thin, conductive layer of copper inside every single one of those holes, instantly turning an insulating plastic tunnel into a perfect little wire. Literally every complex electronic device you own depends on this exact process. So from the rust on a simple fence post to the impossibly complex circuitry in a smartphone, this unseen war on metal is absolutely everywhere. We've developed some incredible science to fight back, basically turning nature's own electrochemical rules against itself. Which leads to the final question. As our technology gets smaller, more intricate, and way more demanding, what new strategies will we have to invent to make sure we keep winning this essential, never-ending battle?